Hello everyone, good afternoon. It's time for class again. This is ECE341, the probability and random process course. Today is the second class. It's a Wednesday of the first week. On Monday, we have go over the syllabus. We also introduce the basic concept random experiment. Right, what is a random experiment? A random experiment is a kind of experiment which will give you several possible results. Right, the final result is just one, but before you get it, you know there should be several possible results. The things like you throw a dice, then 1, 2, 3, 4, 5, 6. You know you have several possible results. The result will be just one of it. Right, one of those 6 numbers, but they have 6 possible results. So we call these kind of things a random experiment. Now let's go more detail on it. This is a ECE341. The first week of Wednesday's class. First week Wednesday's class. Okay, so we consider a random experiment, random experiment. Random experiment. Then we will have a sample space. Sample space, which we denote it as capital S. It is just all the possible results. All possible results. Right. So this is sample space. We call this a sample space. The example we use. Example, we have. If you use a dice, then S will be 1, 2, 3, 4, 5, 6. Okay. Now we consider another concept we call the event. Event. What is the event? Event will be a subset of the sample space of S. I still use dice as the example. Like B1 equal to 1 and 2. So this is the event. We can have a name. We call this as a small. Right? We call it small. You get 1 or 2. That means you get a small number. B2 is 5 and 6. This is related with a large. So the things is like, E, sorry. The things like if you get 1, then B1 happen. You get 2, B1 happen. Right? So this is not just the single result. You get 1 or 2, both cases you can think B1 happen. And another side you get 6 or 5, you think B2 happen. And we can also have like letter B3, which is 1, 2, not 1, 2, 1, 3, 5. So this is kind of odd numbers, right? You get odd number. And B4, here B1, B2, B3, 4, B4, they are just the name of the event. You can use different name. You can give them some name, right? You can use different name. Here I just use B1, 2, 3, 4. The B4 2 is 2, 4, and 6. So this is a even numbers. The event is even. You got an even number. So all of these, they are event. They are event. And S itself is also an event. Right, the largest event. This event always happen no matter what is the result. You do the experiment, then the result may be 1 to 6. Always happen, right? Always happen. Right. Like, okay, for example, we can try. Now I have a dice here. I will see which one will happen. I get 4. Okay, I get 4, then which result happened? B1? No. B2? No. B3? No. B4? Okay. So we got 4. Then B4 happened. S also happened. It's always happen. S is always happen. Okay. Then we can try more. I get 2. We got 2. We got the 2. Then 2, which one happened? B1. I have 2. Okay, so B1 happened. B1 happened. B2? No. B3? No. B4? Okay, B4 happened. And S, okay, S happened. No space, anyway. Yeah. So things like that. You have a result. If the result is a part of the event, then we say that event happened. If the result is not the part of, not the number inside the event, then that event didn't happen. Like when you get 2, you will say the B3, the odd event. Do we have it? No. This one didn't happen. Right. Okay, so this is the event. This is event. And then we can consider the operation of event. Operation of event. So when you have several events, you can consider to combine them to get some new event. So we can have the operation on event. Okay, we suppose A, B, they are events. We have 2 events. Then we can define some different events based on A and B. The first one, A union with B. We use this name. And the union, right? This is a union. Union of A and B. It contains how to say, the both, contain both, it contains all element of both A and B. A and B. Okay. So I still use the example. If I still use a dice, okay. If A is 1 and 2, and B is 1, 3, 5. Actually, the small and the event, right? A small event and the odd event. Then A union with B equal to all the element of both A and B. So we have 1, 2, 1, 3, 5, right? 1, 2, 3, 5. So this is a union. This is union. And for the happen, in which case they will happen. I will say A union with B happen. It will equivalent with A happen or B happen. A happen or B happen. Like for example, if we get 1, okay, now I get 1, so B happen, or both A and B happen, so A union B is also happen. If I get okay 2, then A happen, right? B didn't happen, no 2 in B. However, A union with B contain 2, so A union with B happen. So in this case is A happen, but B didn't happen. Then we say A union B, it happened, right? A union B is A happen or B happen. So one of A and B happen, or both happen, doesn't matter, right? Okay, so this is a union of 2 events. The notation and the name is coming from set derivative. Yeah, it's a part of the math. If you are familiar, then that will be fine. If you are not so sure the meaning of them, you can just read the textbook very carefully. Go over the section, forget section 2.1 or 1.1. Yeah, you can check. I put in the blackboard. All right, which section you can read. They give you more details about the set theory. But if you're familiar with about it, you can just go over it. Okay. Now we look at the second operation. We denote it as a like this one, intersection. Okay, so this is an intersection. Intersection of A and B. So what's the meaning? It contains the element how to say, they belong to both, which belong to both A and B. The common part of A and B, right? Common elements of A and B. Yeah, I can use this way to describe. Then, I still use that A and B. If A is 1 and 2, B is 1, 3, 5, then what is the intersection of A and B? There will be the common element of both, right? So it's just one element. Okay, this is the intersection. And for the happen, we say A intersection B happen. That means A happen and B also happen. Both happen. So you can compare with the union. A happen or B happen. So might be both happen, might be one of it happen. And A intersection with B. The A intersection B happen, that means A happen and B happen. Both happen. Okay, so this is a intersection. We can also use a graph to show it. Like this is a sample space. If this part is A, this part is B, the A union with B, it looks like this. This is A, this is B. The comma, the union, the union of both. And the intersection, if this is sample space, you have an event A, you have another event B, then the intersection is here, the common area, common part. Right. So this is a second operation. And the third one, we can have a kind of a minus, right? Subtract. You remove the element from A and based on B like this. That's still okay. Third one. So A minus B. Now you can also just write A minus B. The same meaning. Alright. It will be the element in A which do not in B. In A but not in B. Okay. And the example. I should use A equal to 1 and 2, B equal to 1, 3, 5, then A minus B. It will be the element in A but not in B. So what it is? It is 2. It is 2, right? You can also think you remove B from A. So B is 1, 3, 5. Here you remove 1. No 3, no 5. Right? So they already removed. No, we do not have it. So you only need 1. After you remove 1, you have 2 left. So this is a 2. Alright. Then for the event happen or not, so A minus B happen. That means A happened. But B didn't happen. A happened, but B didn't happen. So like here, if you get 2, that means A happened, right? A has 2, so A happened. But 2 is not part of B, so no B. B is not happen. Then A subtract B is just that 2. Right? So A happened, but B didn't happen. Okay, the third one, and let me see, 1, 2, 3. Okay, the fourth. Fourth is still subject. But it is I use S to minus the event A, and this one we have notation. We denote it as AC. It's a complement of A. Complement. The C means complement of A. If we use a graph to show it, this one is like this. If this is A, then S minus A is this part. This is S. S minus A looks like this. And this subject we can also use a graph. If this is A, this is B. The A minus B is this part. A, remove this part. Remove B. You remove B, then you get this part left. So this is A minus B. Okay, and I still use the example. A is 1 and 2. Then A, the complement of A is those. S, remove A. S, we have 1, 2, 3, 4, 5, 6. I remove A. I remove 1 and 2. So we only have 3, 4, 5, 6. Right? We remove 1 and 2 from S. And B, we know B is 1, 3, 5. Then BC, the complement of B will be, all the rest element. Remove B, then you have 2, 4, and 6. S, remove B, you get this. Okay, so this is a complement. Alright. And then we can sometimes, you need to combine several things together, and you do some calculation. Then here we have a formula. Maybe sometimes it will be used somewhere. So A union with B, we do a complement. It will equal to A complement intersection with B complement. And A intersection with B do complement, it will be A complement union with B complement. So these two formulas, like here's a union, and here's an intersection. Here's an intersection, here's a union. So these two formulas, they are kind of dual, dual functions, dual each other. And okay, here's a C, here's a C for each. Right? Here's a C, here's a C for each. Inside here is a union. Then here will be intersection. Here's the intersection. Here will be union. All right. Okay, so we have a law related with the operations. And for C, we have another one. For S, we know S is a event, right? So what is the complement of S? Okay, this is nothing. We use this notation to denote it. It is empty. Empty set. Empty event is impossible result. There's something impossible. It's empty. It can't happen. You always have a result, right? This is no result. That means no result. No result. Okay. So this is the complement. Okay. Other than this, we have intersection. We have union. We have subtract. We have the complement, right? The whole sample space subtract the event. Okay, we have these four. I think they are all the operations. You can compare my notes here with the textbook to see, do they have more operations? I think these four will be enough. Okay. This is the operations. Then we can have event. We can have an event space. Another concept, event space. Another name is just partition. Partition of the sample space. You can also just call it as a partition. Just call it as partition. What it is, things like this. You have a sample space S, then you separate the sample space as several parts. Okay, I give name each one. This is B1, B2, B3, B4, B5. For example, I separate S as these 5 small events, the small part. Then each BI is an event. I run from 1 to 5. But in general, here might be depend, right? You can separate it in 5 pieces or maybe 50 pieces. Depend. You can change how many pieces. You can use different way to separate the sample space. Okay. Secondly, the union of all these BI. I run from 1 to this 5. This is a notation. It's a union of those BIs. The notation means B1 union with B2 union with B3 union with B4 union with B5. Right? I run from 1 to 5, so B1 until B5 do union. So this is a notation. The meaning is just like this. Then if we combine all of them together, it is what? It is a whole sample space. And third one, intersection BI intersection with BJ. You pick any two. You consider the intersection of both. Intersection of both. You pick any two. You consider the intersection. Do you have? There's no intersection, right? Any two, they are different. They do not have common area. So the intersection is just nothing, empty. If I do not equal to j, of course, if they are same, then the intersection are themselves. Okay. So we have these three features, and we call it as event space or partition of the sample space, or just the partition, just partition. This way, we, this kind of things we always use it, especially in the case, for example, I consider okay, I use an example. This time the result will be not listed few result, right? The dice we can list the value 1 to 6, right? Separate 1, 2, 3, 4, 5, 6, totally 6 different values. But sometimes you will have the value that is continuous, or maybe you still separate, but you have a lot. So we can consider like this one and use consider temperature. Temperature of tomorrow. Temperature tomorrow. The highest. Okay. The temperature may be different every day in the same day, but the temperature different, right? We consider highest temperature tomorrow. What it will be? Okay, the sample space, you can say it is, well, I don't know, but will be similar with today and with some change. So I can think like from 30 to 45, all right, like this. This means an interval from 30 to the temperature T, temperature T between 30 to 45. This is sample space. Then this is kind of experiment, right? But not performed by you. You performed by the nature. So tomorrow, like around noon, around 1 o'clock, 2 o'clock, you will know the temperature. What is the height? What is the temperature there? That will be the highest temperature. Okay. In most cases, yeah, that time. Maybe some different time, but anyway, yeah, you can have the highest temperature. It will be a number, suppose between 30 and 45. It works, right? Nowadays, if in the summer, like you can have the temperature between, for example, from 80 to 90, or even from 80 to 100, something like that. Okay. Yeah. If you consider the temperature of the whole year, you randomly pick any day and what is the highest temperature of that day, then this one you can think it's between 0 to 120. Did it work? 0. Yeah, it's Chicago. How about the coldest weather? It should be 0 degree. Very few cases, right? Anyway, so okay, just tomorrow's temperature, highest temperature. Then this is a kind of a random experiment, and the result will be in the sample space, which is the interval from 30 to 45. Okay, then when you study, between 30 to 45, you have infinite values, right? Between how many values between these two? Infinite. So for convenience, people usually separate the date in several pieces. So we can let B1, for example, B1 is 30 to totally 15, right? 15. So I use 30 to 35, and okay, not this way, more detail. It is a 30 smaller than temperature, smaller than 45. This side I can make it can equal. This side cannot equal. Okay, B2 is from 45, include 45. T smaller, larger than 45, but smaller than, oh no, not 40, 35, sorry. 35. Then 35, I separate it, 35 to 40. And then B3, which is 40, include 40 to, okay, also included 45. Okay, the whole from 30 to 45, I separate it as 3 pieces. Here's this is 1. I use this way. This way means I do not contain 35. And the second interval is from 35 to 40. And the last interval is from 40 to 45. So we have three B1, B2, B3. It's B2, B3. We have 3 events, and these 3 events, they form a partition, right? It is just a separate of the whole sample space into 3 parts. And if you want, you can also check with more details, step by step. Each BI is an event, no problem. The intersection combine of all of them, union all of them together, you get whole sample space, no problem. And the intersection of any 2 of them is empty. So you see, they do not have intersection. Here I use this is smaller than, this side is larger than and smaller than equal. So I separated the whole space in this way, make them do not have intersection, right? This is small, this is equal. Okay. Yeah. Then we say B1, B2, B3 is a partition or sample space, or partition of the sample space, or the event space. So this is also an event space. Event space, so not sample space, sorry. Event space. Event space. Alright. So this is one more thing. Okay. Then for the partition for the event space, we have 3 features, right? So these 3 features, yeah, let's go back. These 3 features, actually the 2 and 3. These 2 features, we can generalize these 2 features. So we can consider the case we have several events, the union of them equal to the whole sample space, but just this condition. That is a case maybe we have, maybe we do not have the 3rd one. So some of them, the intersection might be not empty. Okay, so we have a concept related with these. We call this is a collective. Let me see. The union is a whole space. So collective exhaustive events. That means several events, B1, B2, until B some K, and they satisfy B1 union with B2 union until union with BK is the sample space, whole sample space. Okay, so this is we call it a collective exhaustive. The same is like I use this as B1, B2, and B3 is this one. This is B3. Alright, then B3 has an intersection with both B1 and B2. So it is not a partition. The B3 contain more element, and the union of them is still whole sample space. So this is the case. It is a collective, exhaustive event. It is not a partition. It is a kind of they have common area. They have some intersections. Right? This is collective, exhaustive. And another case is if we have the third one. If we have third one, we do not have second one, but we have third one. Then this is the case we call them mutually exclusive. Right? It's kind of exclusive. They cannot happen at the same time, and mutually they each other. You consider the relation between them each other. So this is the case we call it a mutually double array. Mutually exclusive event. We have still use event. We still have B1, B2, some event, right? Until some BK. Then this is the case. The intersection of any two of them is empty if I do not equal to J. Right? It's 4. Or I, J run from 1 to K. So this is a mutually exclusive event. Okay, we can consider an example. Which one? I use dice. Okay, dice again. The whole sample space, which is 1, 2, 3, 4, 5, and 6 together. Now, okay, we can have different way to pick up some event, and we can see whether they are mutually exclusive, whether they are collective, exhaustive, or whether they are just a partition. The first one, I choose B1 equal to 1, 2, and 3, and B2 equal to 4, 5, and 6. Okay, what kind of events are they? Obviously, this is a partition, right? I just separate the S. This is S 1 to 6, and separate 1, 2, 3 are here, and 4, 5, 6 are here, right? So this is the case. B1, B2 together is a partition of the sample space. Right. Okay. Second one, we consider like B1 equal to 1, 2, and 3. B2 equal to 3, 4, and 5. And B3 is just 6. Okay, so what can we say about these three events? You can say like this: 1, 2, 3, 4, 5, 6, right? This is sample space. Then what is B1? This is B1. What is B2? 3, 4, 5. This is B2. And this is B3. You can see B1 and B2, they have a common element. So the intersection of these two is not empty. Then we say we do not have this, right? For mutually exclusive, we need the intersection must be empty. But this one intersection is not empty, so it is not mutually exclusive. But the union of these three is the whole sample space. so it is collective exhaustive. So we'll say B1. Okay, anyway, I don't write. You know, we're talking about B1, 2, and 3, right? So we know it is collective exhaustive. I check it means it okay, it is correct. And mutually exclusive. No. Use a cross means no. Okay. And as a sample space, as a partition. No. This is a yes. This is a no. No. Alright. Okay. Can we have any more example? Yeah, you can try. You know, you can separate the whole sample space as several parts and to see which part, which kind of the events there, right? Collective, exhaustive, mutually exclusive, or partition. Okay. Actually, most common use is a partition. Yeah, it's a partition. Okay, so this is for the event. All right. Now we consider the probability. The most important thing is what is the probability. So we say the probability. 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 What is a probability? Probability, it is a number to how to say, to measure the possibility of the event. So that means for every event, for every event, assign a number. Yeah. But basically you need a sign for the possible result, right? Possible result. I explain user. Okay, example. Like you have a coin, then the sample space will contain two possible results. One is a face, one is a tail. Then we can have probability. I use PR for the probability for F. This is the event. This event contains a single value. It is 1. Suppose the coin is a fair one. There will be 1/2, right? Half chance face and half chance tail. And if you consider the probability of the whole sample space, there will be 100%. There will be 1, right? And if you consider the probability of empty set, yeah, that will be 0. I said this is an impossible event, right? This is nothing. So things like that. All the event, you can have the probability. And another example, I consider the dice. The sample space is 1, 2, 3, 4, 5, 6. And then the probability for each number, I say I, there will be 1/6. I could be 1, 2, 3, 4, 5, or 6. And then for other event, you just combine them, right? Like if B is 2, 3, 6. Then the probability of B will be the probability of 2 plus probability of 3 plus probability of 6. So it's 1, 6 plus 1, 6 plus 1, 6 is 1/2. Things like that. Right? You just combine them. Like each element, you have the probability. The add them together, you have the whole probability of this event B. Okay, here's the problem. How can you get these? And how can you get these? You know, these two are basic things. You have half and half for each event, each simple event, each possible result. Here's also for each possible result, you know this is 1/6. How do you know that? Okay, I will say this is kind of experiment. And generally, I will say it like this. How to say? I will say you have experiment. You repeat the experiment. The things like this. Okay. We have a law. Yeah, the Bernoulli's law. Bernoulli is a law of large number. We repeat an experiment n times. Then record the times m of event A happen. Right, A happen. How many times A happen? Then, like this is M. Totally, we do n experiment, and A happen n times. Then we have a kind of rate, right? M out of n. Okay, this one we're close to P, probability of A. And furthermore, we have the limit when n go to infinite. If you do more and more experiment, then this m over n, the limit will be just the probability. So like the coin, you have a coin, right? You say okay, you think both sides will occur equal likely, each is half possible, right? Each side is half. So that means if you, for example, you try 100 times, there are about 50 has face and another 50 has the tail. If you try like 10,000, then you have 5,000 ways tail and 5,000 ways face. But maybe a little bit different, right? Maybe you have several more times for face or several more times for tail, depend. But the limit, if you do more and more times, this limit will be the half percentage for each one. Actually, we do this, everyone do this, right? This is experiment work not just by one person. All of us try this several times. Maybe someone never do it, but he knows someone else do it. And year by year, always some people try this. Then, okay, all of us, we know, okay, this is half and half chance. And for dice, we know it's each side is possibly with same possible. So each side is 1/6. Totally is 100%, right? Each side is 1/6, one out of 6 possible. And if you are considering some experiment which is not so fair, right? They are fair. Each side is the same, equal likely, probably they're equal likely. If you consider something they are not so fair, now how to determine the probability? You can try just like this. You repeat the experiment with large number times, and larger the or better. Then you record how many times A happened, the m over n. That give you the probability, the approximate of the probability. Alright? Okay. Then that's all for today. Okay, 15 minutes. Okay, just on time. Okay, then see you next time. Bye bye.